Chapter 9, Section 5, Inner Product and Vector Space. In this section, we will learn how inner products change the meaning of a vector space. They are not just rules for calculation. Inner products reshape how we understand the structure and behavior of vectors. Specifically, we will learn about how inner products define angles and length in vector spaces, how they enable us to talk about projection and orthogonality, how they give geometric meaning to algebraic structures, and how inner products lead to the concept of Hilbert spaces when combined with completeness. In mathematics, a vector space by itself is an algebraic structure. It tells us how to add vectors and multiply them by scalars. But by default, it does not tell us anything about angles, length, and distances. In that sense, it is blind to geometry. Now, once we introduce an inner product, everything changes. The inner product gives the vector space a sense of geometry. Let's take a closer look. First, the inner product enables us to define length or norm in this way. Now, vectors have magnitudes. Second, it enables us to define angles between vectors using the cosine formula. This gives us a way to talk about directional similarity. And third, it lets us define orthogonality. Two vectors are orthogonal if their inner product is zero. This concept of perpendicularity becomes a foundation for projection, decomposition, and more. So, by adding an inner product, a vector space becomes more than just algebra. It becomes a geometric environment. The space is now equipped to express shape, angles, length, and structure. So far, we've explored what inner products enables us to do: measure length, angles, and define orthogonality. Now, let's go on to a concept named inner product space. Let me show its formal definition. An inner product space is a vector space V over R or C, equipped with an inner product that can be written in this way. As this expression suggests, an inner product is a function. That means it takes two vectors as input and gives a real number or a complex number as output. The inner product satisfies the following three key properties: linearity in the first argument, conjugate symmetry, and positive definiteness. Now that we've defined an inner product space as a vector space equipped with an inner product, let's look at what this structure gives us, specifically norms and metrics. First, from inner product to norm. In an inner product space, the first measure tool we get is a norm. This measures the length or size of any vector. The norm of a vector V is defined using the inner product. This works because the inner product of a vector with itself is always non-negative and zero only for the zero vector, thanks to the positive definiteness property. Second, from norm to metric. Once we have a norm, we can define a distance between two vectors, which we call a metric. The distance between u and v is just a norm of their difference. It can be expressed in this way. Now that we have seen how the inner product introduces the geometry, we can define a new type of space, an inner product space. An inner product space is simply a vector space equipped with an inner product. But this seemingly small addition leads to a big transformation in what we can do. Let's look at what changes. First, let's talk about angles and orthogonality. This opens the door to tools like orthogonal projection, dropping a vector onto a subspace, orthogonal decomposition, breaking a vector into orthogonal components, Gram-Schmidt process, turning any basis into an orthonormal one. Second, the inner product induces a norm, and thus a metric. This means we can talk about convergence, limits, and continuity, concepts that are not even defined in a plain vector space. Third, inner product spaces support geometric reasoning. We can speak of nearest points, angles between subspaces, and projection with mathematical precision. So, in short, an inner product space is no longer just a set with algebraic rules. It becomes a geometric and analytical environment where we can measure, compare, and decompose vectors in deep ways. Let's wrap up. An inner product space is a vector space equipped with an product that satisfies linearity, conjugate symmetry, and positive definiteness. The inner product induces a norm, which induces a metric. This gives us the tools to talk about distance, angles, and limits. Thank you for watching. Please thumbs up and subscribe to my channel.